The regular rules of differential calculus apply. Throughout, we have I an interval, C some point in the interval, and then f and g two differentiable functions on I. In particular, they are differentiable at the point C. Then, if you have a real number alpha, then the function alpha f from I to R is differentiable at C. And the derivative of the function at C is the product of alpha with the derivative of f at C. Similarly, the function f plus g defined on the interval is differentiable at C, and the derivative is exactly what you would expect it to be. It is the sum of the derivatives. The product of the two functions is itself differentiable at C with derivative given by the product rule. Derivative of the first term at C times second function at C plus the first function at C times the derivative of the second term. And finally, assuming that g is never equal to 0 over the domain I, over the interval I, then the quotient function f divided by g is differentiable, and the derivative of the quotient is given by the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the square of the denominator. You know all of these from calculus. Now we'll provide a real analytic proof. On the one hand, assuming that the function alpha times f is in fact differentiable, then you would have that this would be the limit when x goes to c of the function alpha f at x minus the function alpha f at c divided by x minus c, which by definition is the limit when x goes to c of alpha f at x minus alpha f at c divided by x minus c, which is itself rewritten by extracting the common term alpha. And if the limit exists, then you can take the alpha, take it outside, and you end up with the product of alpha with the limit when x goes to c of the differential quotient f at x minus f at c divided by x minus c. Only, of course, if the limit actually exists. You can't do that otherwise, right? But we know that the limit exists because f is differentiable at x equals c. So f prime c exists, and if prime at c exists, then it is equal to the limit when x goes to c, f at x minus f at c divided by x minus c. So this expression here is equal to alpha times f prime at c, which gives us two results with one stroke. Not only do we show that the derivative of alpha f at c is alpha times f prime at c, but we also do show that the function is differentiable at c. Now we play a pretty similar game to prove all of the other statements. What can we say about the derivative of the function f plus g? Well, assuming the limit exists, it would be equal to this quantity. That is the definition of the derivative. And by construction, this would be f at x plus g at x minus f at c minus g at c divided by x minus c. So far, so good. Assuming the limit exists, I'm going to rearrange some of the terms. And now, if each of the individual limits exist, this limit here would be the same as the limit when x goes to c of the first differential quotient plus the limit when x goes to c of the second. But we know that these limits exist because f and g are both differentiable at c, so these limits individually exist, in which case the limit of the sum here of the differential quotients exists, which means that this limit also exists, and it has to be equal to, by definition, f prime at c plus g prime at c, the derivative of f at c plus the derivative of g at c. It's crucial that in order to be able to write this here, our theorem on the limit of a sum requires the limits of each of the terms to exist. If we do not have that as an assumption, we can't conclude that this limit here exists. For the product, same sort of idea. what would be the derivative of the product of the functions f and g at c? Well, if the limit exists, it would be this limit that you're interested in. I'll rewrite the products, and then we use a trick that we very often use. We're going to add 0 to the numerator so that we don't actually change the value, but we write 0 in a very specific way, minus f at c g at x plus f at c g at x. This will allow us to rewrite the sum as f at x g at x minus f at c g at x divided by x minus c plus f at c g at x minus f at c g at c divided by x minus c, and we compute the limit. Now, if it happens that the limit of each of these individual differential quotient exists, then the limit of the sum will be the same as the sum of the limits, and we will have demonstrated that, first of all, the product of function is differentiable because the limit exists, and we'll be able to find its actual value. But it does exist. Let me first rewrite the sum of differential quotients by putting common factor out. For the first term, we had g at x that was in common. For the second term, f at c. Now, what we would like to be able to do is to write this as the following expression. The limit of g at x when x goes to c times the limit when x goes to c of the differential quotient plus the limit when x goes to c f at c times the limit when x goes to c of the differential quotient. And we can only write this if it turns out that each of the 4 individual limits exists. Well, we know the fourth one exists because g is differentiable at c, and this is exactly the derivative of the function g at c. Similarly, we know that the second one exists because this is exactly the definition of f prime at c. We know that f is differentiable at c. F at c is a constant, and the limit of a constant actually exists. This is equal to f at c. And finally, we're left with the first one, the limit of g at x when x goes to c. Well, what we do know here is that g is differentiable at c, and what we've seen is that if a function is differentiable at a point, it is also continuous at that point. So the limit exists, and it is equal to g at c. So not only does the derivative of the product exist by virtue of each of these 4 limits independently existing, meaning that this limit here exists, but we also know what the value of the derivative is going to be. It is derivative of the first term times the second plus the first term times the derivative of the second term. But this hinges on Theorem 39. If a function is differentiable, which it is by assumption, then it must be continuous at the point of differentiability. And finally, we show the quotient of function, assuming that the denominator is never equal to 0, is in fact differentiable. There's many ways to do this. I'm going to use the limit argument. You could also basically show, if you call the quotient of f by g h, then you can write f as g times h and basically apply the product rule. So the assumption here is that the function g is differentiable at c, and hence in particular it is continuous at c, and also that g at c is not equal to 0. Now we know that that's the case because by assumption g at x was not equal to 0 over the interval I. So what are we interested in? Well, we're interested in the quotient, and we want to know something about its derivative. If the derivative exists, it would be given by the limit of the differential quotient. Let's rearrange some of the terms before we do any computation with the limit. So I have f at x divided by g at x minus f at c divided by g at c divided by x minus c. I'm going to put everything here on a common denominator. So I haven't really done anything here. I've just reorganized the terms inside of my limit, and I'll basically use the same trick as before, except I'm going to use a slightly different way of writing 0, the 0 that I'm adding to the numerator, and we'll add it as minus f at c times g at c plus f at c times g at c minus f at c times g at x. I can simplify this further. I'm going to take the denominator g at x, g at c, bring it out here, and then rearrange the terms. So I have f at x times g at c minus f at c times g at c. So there's a common term here, just g at c. And I'll do the same thing for the other side. There's a g at c minus g at x. So for now, I'm actually going to write it like this. I need to have the x's showing up on the first term here. That's not the one that I have. But I can easily remedy the situation by multiplying here by -1 and changing the order of the terms in the numerator. So now, assuming that every single one of these limits exists, this would be the same as the limit when x goes to c of 1 over g at x, g at c, times the limit when x goes to c of f at x minus f at c over x minus c, times the limit when x goes to c, g at c, minus the limit when x goes to c of the common term here, 1 over g at x times 1 over g at c, times the limit when x goes to c of g at x minus g at c divided by x minus c, times the limit when x goes to c of f at c. Again, assuming that each of these individual limits do exist, because if they do here, then this limit exists, and if it exists, that means that the derivative of the quotient is then well defined. We will have proven the theorem. But what do we know? We know that this one exists, and it is equal to f prime at c. We know that this limit here exists, and it is equal to g at c, right? This is not affected by what happens to x. This is a constant value. This one exists because g is differentiable at c. This one exists for the same reason. It's equal to f at c. And we are left with this limit right here. 1 over g at x times 1 over g at c. Let's just work on this for a little bit. So we're looking at the limit when x goes to c of the product of these two functions. Assuming that each individual limit exists, this would be equal to the product of the limits. Well, we know this one exists here. 1 over g at c, that's a constant. It's defined because g is not equal to 0 on the interval I. So this one is defined. So we need to worry about this one here. So how do we work with this? Well, it is going to be the limit when x goes to c of 1 divided by the limit when x goes to c of g at x and times the limit when x goes to c of 1 over g at c, assuming that each of the limits individually exists. We know this limit exists, it's a constant, so that's equal to 1, we're happy with it. This function g here has a limit at c because g is differentiable, hence continuous. So this little chunk is g at c, and the limit of 1 over g at c is 1 over g at c. So we've managed to show that each of the limits here exist, meaning that the limit of the product exists, meaning that the limit of the actual terms here and here do exist, and hence that this limit exists, and so that the function f divided by g is differentiable at c with an actual derivative equal to f prime at c times g at c minus f at c times g prime at c divided by the square of g, which is the typical rule for differentiation of a quotient. And that concludes the proof of the theorem. If you're like me, you're like, oh man, do I really have to do this for every... You do, right? I mean, if you want to be able to use the theorems that allow you to distribute the limit operator to the various components, you need to make sure that the assumptions of the theorem are satisfied. By mathematical induction, you can show that the results here extend the cases where you have a sum of more than two functions or a product of more than two functions. The derivative of a sum of functions at a given point c, assuming that each of the individual functions was differentiable at c, is the sum of the derivatives, and the product of functions has a derivative. Well, this sum here is a little bit less obvious to write. You're going to start by differentiating the first term, then leaving the other terms and the product undifferentiated, plus the same rule as a whole, except it is the second term that is being differentiated and everything else is undifferentiated. Finally, you have the product of all of the individual functions being undifferentiated and the last one being differentiated at c. Again, this is only valid if each individual function is differentiable at c. There's a special case here if each individual component is identical to all the other ones, then the derivative of the product of each of the functions will be the derivative of the nth power of the function, and it is going to be the same as n times the n minus 1 power of the function f. Now be careful, sometimes we use a notation between round brackets here to mean that we're talking about the n minus 1th derivative. Without the brackets, we're talking about the power times the derivative of the function. If the function f is just the identity function, then what this is telling us that the nth power of x would be x to the n, and that the derivative of the nth power at c would simply be n times n minus 1th power times the derivative at c, that would be n times c to the n minus 1 times the derivative of the function identity at c, which we haven't yet shown, is equal to 1. Once we do, we're going to get this very specific rule here. Of course, c could be equal to x. C is any value in there, so it might make more sense to write it with an actual x. This gives us the derivative of the power function.